Okay, I'm going to present a work that was performed mostly by a PhD student, Mukhtar Bello, who now defended, and co-supervised with my colleague Arsenia Shorty from ETIS, which is an UMR in Cergy, joint research lab between CY Cergy-Paris University, NCA, and CNRS. And as you may notice, CNRS provide us some real nice tools to keep warm these days, which is really nice. Okay, the slides don't want. Okay. Nope. Yes. Okay, so I'm going to talk about uplink NOMA systems and what will be different from some of the talks that we have seen earlier is that we're going to try to take into account some delay constraints that will take into account especially what's going on at the link layer. And when we will do that, we will define the two metrics to measure these things that will be effective capacity and effective rate that I will introduce after presenting the system. Okay, so the idea here is to consider a system which has possibly many users like MMTC context, and that is why we're going to consider the users in the uplink and with the non-orthogonal access, just to put the context of the talk. The system that I'm going to consider will consider the base station, the received signal, Z here, which is the sum of the superimposed signals coming from K users with NOMA power coefficients. I will call them alpha. I will have a constraint total power. That is one of the assumptions of this work. And I will consider the users ordered by their channel gains. This is just a technical assumption, but I will need that in the derivation. Then the transmitted signals are usual transmitted signals and complex circular noise on the system. We're going to assume that we have perfect channel state information, superposition coding, an ideal successive interference cancellation. All that was introduced by Jean-Marie this morning, so I hope that you all remember all these items. And at first, I will consider the asymptotic regime in terms of the block length. And in that case, the NOMA throughput is usually considered as this well-known formula that we have seen many times, where gamma defines the signal to interference to noise ratio, and which will take into account the power NOMA coefficients, the alphas that we have. Usually when we look at power allocation in the physical layer, what we look at is to find the alphas to do power NOMA so that they will maximize, for instance, the scan rate given some constraints. And one of the constraints that we will consider here is that the rate is higher than the rate related to the OMA system. And we consider in terms of fairness that the OMA system will divide its rate between the different users equally. Okay, I'm not going to do the power allocation in the at the physical layer because this is already known things and it's not what we're interested in. A few remarks about this system. One is that I've said that we want to consider the seek to be ideal, but we know that this is not true and really far from being true. So we need systems where we don't have many users to be able to perform a good signal interference cancellation. Okay, so what we're going to use here is mostly a two-user system. And if we want to divide our system with pairs of two users, that involves that we will have also pairing, that will put the users by pair of two. And then for each pair, we will do all what I'm talking about. And between the pairs, we assume that the system is totally without interference, which is kind of true if the pairs are far away from each other. So we can assume that we can have this kind of system. Actually, in the work, we have also looked at systems with 3 users, but we don't think that because of the seek, we will be able to do more than 3 users. It's not very reasonable. And also the questions I'm going to deal with become kind of too large to be able to be really reasonably handled. In this talk, I'm not going to talk about the user pairing, but it appears in the paper. Also, I'm not going to talk about the robustness to the channel state information, but it's kind of okay. I will talk in the second part of the talk about the finite block length system, assuming the Poliansky approximation, as we have seen also earlier this morning. Okay, what I'm interested in is to try to see how we can look at the system from the link layer, and especially in terms of latency. Okay, so if we look in terms of latency and what's going on, what is defined the U-plane latency in 3GPP is the time to successfully deliver an application packet through the layer 2-3 via the radio interface in both uplink and downlink. We're going to consider only here the uplink part, but still that's what we are looking for, assuming that there is no discontinuity in the reception. Okay, this latency, it's defined as this time, the time through the radio, the time of the backhaul, the time of the core and the transport, but we're going to focus on what's provided through the radio system. And what we see here is a duration for queuing, a duration for the frame alignment that we assume to be fixed, also the time for the payload transmission and the transmission processing. We are not going to consider them, and what we are looking for here is the queuing at the link layer. And the tool that has been proposed to do that is the effective capacity. Okay, so I assume that not everybody is aware of the effective capacity, so I'm going to spend some time on defining that. The effective capacity was proposed by Wu in 2003, and it assumes that we have source rates that are given by some quadrate. They assume that we have a buffer at each transmitter that is defined by a Markovian transmit buffer that takes into account how the queuing arrives, like one packet after the other. And the physical channel is a fast padding wireless channel Rayleigh model for what I'm going to present, but it can be extended to other kind of fast fading wireless channels. Given all that, and yes.
Since you will discuss in Q&A, so I mean, when you say source rate mu, you mean like packets arriving at rate mu, like Poisson point processing?
Yes.
Like that? Okay.
Yes.
Thanks.
That's really what is in the paper by you. Okay, so what they defined is that for a user that wants to achieve a given rate of R, a bandwidth B, and a fixed duration of the block fading that we call TF here, they define the effective capacity as this expression that you can see, which is like a normalized version of the log of the mean expectation of the expectation of minus theta times this time frame, bandwidth, and rate. Okay, if you look at this expression of the effective capacity, if you consider the channel as being fixed, so the mean expectation over h cancels, and indeed the log and the exponential cancel out, and what you find is R. Okay, so if you look at this expression, if the channel is static, we find again the rate. I like this approach. I mean, to have that in mind, because this is what it really shows, that this effective capacity looks like a capacity for a fixed channel. Now, if the channel is not fixed, which is the case in general, what we need to take into account is this mean expectation over h. And that is what we need to calculate here, is really to take this mean of expectation over the channel statistics. And we are going to see how it behaves. Okay, so you can see that the terms in the fraction before the log is just here to normalize this expression. The term that you don't know so far is the theta here, and theta is this is called the statistical delay QS exponent, and it can be defined as the limit for the log of the probability of the steady state transmit buffer to go to infinity divided by x. So it's really defined as a delay exponent. Yes.
Je profite pour cette question et là, que ça se fixe.
Okay.
Donc il y a h, et quelle est la variable qui dépend de r, de h?
H is the channel, and the channel is the rate is the function as the instantaneous signal to interference ratio, and so it depends on the h, on the statistic of the channel.
Ok, R c'est 1
R
plus SNR.
R is the usual
Okay.
throughput, which depend on the signal to noise ratio. So it depends for the different users on the channel statistic. So the thing is that, as you may see, because of the ideal seek, for R1, we have something which is quite simple because it depends only on the h square channel gain, usual. But as we go for the weaker user that are going to have to decode with some remaining interference, the strong user that has to decode through remaining interference, we have the signal to interference and noise ratio, which depends on both the statistics of H1 and H2. And that is what is a bit complicated in terms of the derivations. here. Okay. So theta here can be viewed as this statistical delay QS exponent. And I must say that it's quite difficult to relate this theta to really values of latency on the system. It's really, to me, one of the difficulties of that theory. But what is clear is that if you look at in terms of outage delay, you can see that it is proportional to the exponential of this theta times the delay, the maximum delay. So we really see that this theta has impact in terms of measuring the delay of the system. Just to give some interpretation of that, when theta goes to 0, we have a system that will be very delay tolerant, and on the contrary, as theta grows, we have delay stringent applications. And these are the situation in which we really want to make sure that the system is able to take into account these delay constraints. Just in terms of notation, we define beta as the normalized QS exponent, and because of this sign, the minus, beta is a negative value. So on the contrary, for delay stringent application, beta is going to go to minus infinity.
So it's called capacity. So we are used to capacity in queuing theory, lambda less than mu, rho less than 1. Capacity in the Shannon sense, but it's yet another notion of capacity.
Yeah.
And what type of capacity does it represent in conjunction with these two other notions? Just to understand.
Well, it's kind of, I mean, the thing that is important is really that we have this mean expectation in between the log and the exponent. So it really can be viewed as an exponent. The theta is really an exponent QS that relates to the delay. And what really matters is that we have this mean expectation with respect to the channel. But as you can see, this expression is of the same kind and has the same dimension as the capacity, the Shannon capacity expression. So it has the same dimensions, and as I said, with the channel is static, they are similar.
So there is a global assumption that the Q is stable because you discussed that.
Yes.
So there is also the rate and the input should be related in such a way that the queuing capacity is satisfied, and you put the steady state, and this is more of a Shannon type.
Yes.
Okay, thanks. Sorry.
No problem. Okay, one last thing. Indeed, if you look at the effective capacity with respect to the QS exponent, the effective capacity decrease from the Shannon rate, that is like the flat thing on the top, and it decreases, the effective capacity decreases as this theta increases, and as the application becomes more delay stringent. Okay, so now we are going to look at the expression in the case of the NOMA 2 users NOMA case. And I'm not going to go through the derivations, they're all in the paper, but the important thing is really to use ordered statistics, and using them, it's possible to really calculate the expressions of the effective capacity for both weak user and strong user. As I said, for the weak user, it's not that difficult because the weak user, you take the mean expectation over x1, which is like the channel gain of user 1. That's easy, well, kind of easy. And you find a function that depends on beta, which we said that beta is this normalized delay exponent. And we have a function that is the confluent hypergeometric function. So it's kind of a complicated function because it defines through some integrals, but it's, well, I mean, it's easily calculated. For the strong user, it's more complicated because we need to take the mean expectation on the channel gains of user 1 and user 2, so x1 and x2. And so you need to do that through the PDF of the joint distribution of the two channels. And it gives an expression that you can see. It's kind of, it starts to be not so easy expression, but it's a closed form expression. There is no approximation here. And it depends this time about the gamma incomplete function. And it depends indeed on the power NOMA coefficients of both users. Okay, so we got this closed form expression. It's not a very nice expression. It's kind of difficult to interpret, but it's there. What did we try to do about that? We tried to see how it looks in terms of the effective capacity first. Yes.
Excuse me, I'd like to continue because I'm not sure I understood your answer to François' question. You can compute EC, but what is EC telling us? That's something I missed.
So EC is taking a mean expectation over the channel gains that is related to this delay constraint. So the theta in this expression is
Theta, I understand. That's the term.
Yeah.
The best term of this form.
Yes.
But how is EC related to theta?
So EC, the expression there is the log of the mean expectation.
Formula.
Yeah.
This formula is it's formula.
Yeah.
At the end, if you say to me EC is so much, what does it tell me?
Well, I think that this curve here of the effective capacity tells you that if you don't put a constraint on the delay, the effective capacity goes to the channel capacity. But if you want your system to be able to ensure you that your latency at the layer 2 is not too high, you have a theta that is larger, and so the bound that you have on the effective capacity is smaller. And so what we say is that if we want our NOMA system to be able to transmit with some constraints on the latency, we need to ensure that the effective capacity maybe is higher than some value or is maximized.
It's an index that tells, but it's not directly related to channel rate of transmission or a delay or something.
No. That's what makes it a bit complicated, I believe. Okay, so I'm going to show you that it is important to do power allocation in that case, and the power allocation that we do is not always the power allocation that we think of at the layer 1. So here, what you can see on this curve is for fixed power NOMA coefficients. So we fixed arbitrarily alpha 1 and alpha 2. And we looked at both OMA and NOMA systems. And what we can see here is that the effective capacity of user 1, yes, is not increasing as we liked it to do with respect to the transmit SNR. And that tells us that if we look at this effective capacity, NOMA doesn't always outperform OMA. And so we need, if we want to be able to say that NOMA is doing better than OMA, we need to do better in terms of power allocation. So here what we do is that we optimize the sum capacity with respect to this power NOMA coefficients. And well, we find cross-form expressions, especially for low and high SNR. For intermediate SNR, it's difficult to find cross-form expression. And you can see that these expressions are indeed a bit complicated, but they do exist. When we don't get closed form expression, what we try to do is really to average the layer 1 power allocation, because we don't know to do better than that. What we can see is that, especially for ISNR, this power allocation gives some great improvement. For low SNR, we have some improvement, but it's not so important. Okay, I'm going to go quickly. One thing also to be noticed is that when theta becomes really large, sometimes we cannot have a solution to the problem. And that means that in that case, it means that NOMA is not able to outperform OMA, which is also one of the things that we can conclude here. It's not always possible to, at the same time, for NOMA to achieve, to be able to outperform OMA, and at the same time to ensure the delay stringent application. So we cannot gain on all the places at the same time. Okay. Very quickly, and I'm not going to go into details. Effective rate. The effective rate is defined by combining both effective capacity that we have seen earlier and Poliansky approximation in the finite block length system. So I'm not going to go, I mean, we have talked this morning a lot about the finite block length system. So you can see that just the system is defined, I mean, the effective rate is defined exactly in the same way, just that we add, instead of the rate, we take Poliansky approximation at the first order. Also, we want to see approximation of the terms of the square of V for with respect to gamma, so the SNR of the system. So we can have approximation for low and high SNR. And we're going to basically perform the same thing as earlier. So the expression of the effective rate are kind of big like that. So I didn't try to put them on the slide. I mean, it's anyway unreadable. But again, if we do approximations at low and high SNR, we have solutions, especially for the ISNR regime, where we can find the best power NOMA components. So the expression is not very nice, but it's there and it really exists. One remark is that for low SNR, it's not possible for the NOMA system to outperform OMA, because for low SNR, it requires more power to outperform OMA. So there is no solution to our optimization problem. We cannot have the NOMA to outperform OMA. And one thing, if you notice, is that we really have different conclusions for the block length system, for the finite block length, than from the infinite block length. And that's also one of the things that I found quite interesting, is that we really have different different solutions in different cases for which we cannot solve the system, and NOMA definitely cannot outperform OMA when we are in the finite block length than if we look at the infinite block length, which is also one thing that we didn't especially expect. Okay, these were just simulations to look at that, and I'm going to conclude. Well, all the take-home message from this is that if we want to be able to do low latency systems, we need to be able to take into account latency in different aspects of the system when we consider the different metrics. This is things that Jean-Marie said at the beginning of his talk, and I really agree with that. So I'm not saying that here we take into account all what is related to latency, really far from that. As you have seen in the latency in the EU plan, we have different terms and we didn't take into account the other terms. But at least with this model of the queuing of the buffer of the users, we take into account some of the aspects that are related to latency, and that effective capacity and effective rate allow us to express these metrics and to optimize the NOMA system. And I think there are a lot more to do on that. One of them is to really revisit all that is related to user pairing. You have applications to NOMA relevant, which is a system in which you have the best choice between NOMA and OMA, which is also one solution for this kind of system. And more recently, some colleagues have looked at how to ensure secrecy capacity using this same kind of metrics. Thank you for your attention.